All right, today and for the rest of Chapter 6, we're going to be talking about quadrilaterals. So we looked at kind of some refreshers on polygons. Now we're going to get into specifically four-sided polygons and all the different varieties that they come in. This video is just going to be an overview of the general family tree of quadrilaterals, kind of like we had for triangles, where we classified triangles by number of sides that were equal or their angle measures. We had like isosceles, equilateral, obtuse, acute, right. Those kind of classifications, we have a similar thing for quadrilaterals, but it's a more complex family tree because with four lines we can make a lot more interesting choices about how to constrain things. Triangles are very limited because it's the absolute minimum number of lines to make a polygon at all. So within quadrilaterals, the most basic kind of quadrilateral would be one with nothing kind of related to anything else. So, and here we're talking about convex shapes because concave ones are weird. So if I have a polygon that is four sides, but every side, let's say, make this one here and this one here. Every side is a different length. None of the sides are like parallel or perpendicular to each other. It's just kind of a four-sided shape. It doesn't have any special properties. There's no math that we can do with it. So this is kind of our unconstrained, most basic quadrilateral. But within quadrilaterals, we have a couple of main classes. One is called parallelograms. So parallelograms are where we take a quadrilateral and we geometrically constrain the opposite sides to be parallel to each other. So think about when we did transversals, if we had two pairs of parallel lines that cross, the shape in the middle here would be a parallelogram. And we found out that when two sets of lines are parallel, we end up with matching angles at all four of these intersections. So this parallelogram living here in the middle is created by those parallel constraints. So we have parallelograms as a major subfamily of quadrilaterals, and they have two congruent side pairs. Actually, let's just go ahead and say they're congruent and parallel. So two congruent parallel side pairs. So that's kind of one of our really important shapes, and then there's more mathematical properties within those that we'll get to in a separate video where we're talking specifically about that type of shape. But then within parallelograms, there's a couple of other things we could do. So we saw that with crossing lines, we could make them perpendicular, so that not only do we end up with the same four angles at each intersection, we know that all of the angles, all 16 of these angles, are all exactly 90 degrees. So the shape we end up with in the middle here is called a rectangle, as I'm sure you're familiar. So a rectangle still has this property. It still has two congruent sides that are parallel to each other, but in addition, it has all right angles. So that's kind of an extra property that it has, and that then, as a result, has extra mathematical value and other things we can calculate within a rectangle that we couldn't within just a parallelogram. So a different way we could go, instead of squaring up these lines and making them right angles, we could instead make it so that we have all of these sides equal in length. So let's go back to just two parallel lines. And now we're going to set all of these equal. Sorry, I had to sneeze there. So we're going to set all four of these lines equal. What we get then is a shape called a rhombus. So a rhombus has two pairs of parallel sides, but we're kind of leveling up this two congruent sides to say four congruent sides. So rhombus has all four sides congruent, but it doesn't have this property over here. It doesn't have that all angles are right angles. So we still know some relationships like this angle and this angle are equal, and this one are equal. And again, we'll get more into the individual properties of these shapes as we move forward. But these are kind of like two branches or two ways that we can further constrain a parallelogram. Now, as you know, we can combine these two together and bring them back together, and then the shape that would result from that would be a square. So a square doesn't have any new properties of its own, but it does have all the properties of both of its parent figures. So it has all right angles and all four sides are equal. So I know you're familiar with squares where we have 4 90-degree angles and 4 congruent sides. So this subfamily of quadrilaterals is called parallelograms, but that's not the only special kinds of quadrilaterals that we have. Rather than making these two sets of parallel lines, we could make a shape just by taking any two parallel lines, like these, and then connecting them with two other arbitrary lines. So I could connect with that line and that line. And now I don't have any relationship between these two lines because they're not parallel to each other. But that doesn't mean I don't have other relationships. Like, since these two are parallel, I still know things like these are consecutive interior angles, and so are the ones over here, meaning I know they add up to 180. So kind of another family, if you can recognize this shape, is called a trapezoid. And a trapezoid has one pair of parallel sides. And we'll talk more about trapezoids a little later, but these two sides that are parallel are called bases, and these other two sides are called legs. And we'll get into the properties of these and what we can calculate based on it a little later. But there is a subtype of trapezoid. So trapezoids, we could force these two legs to be equal in length. And if we do that, we call that one an isosceles trapezoid. So it still has one pair of parallel sides, the same as a trapezoid, but now it also has the legs are congruent. So you've probably seen trapezoids that look like that, where it has the two legs look the same, so that's parallel. These are congruent. And basically what that is like we took an isosceles triangle and we just kind of stretched it out to the left and the right and made it wider. So we took the base down here and made it wider, and we took this point and stretched it out to give it some length. So this is kind of a separate branch of quadrilaterals. And you may say, well, isn't a parallelogram a trapezoid? Because it does have one pair of parallel sides. But generally, and definitions do vary, but generally trapezoids are defined as having exactly one pair of parallel sides. So that differentiates them from parallelograms and says that parallelograms are a separate kind of thing. They're not a subset of trapezoids exactly. Although I have seen a few places that define it as being one or more pairs of parallel sides, in which case a parallelogram would be one. But here in our class, we're going to define a trapezoid as having exactly one pair of parallel sides. So not two pairs like that one, just one pair. And then we have another kind of special shape called a kite. So kite looks exactly like a kite. It has two pairs of congruent sides, like that. So this side and this side are congruent, this side and this side are congruent. So two pairs of congruent sides, and those are not parallel. So if they were parallel and congruent, that would be a parallelogram. So the kite is a shape that has these two pairs, and I think it's formally defined as having line symmetry across a diagonal. So if we draw either diagonal of the kite, so either this blue one or this, or we could draw this orange diagonal. So remember, a diagonal connects two non-consecutive vertices. And, sorry, not that one. Not the orange one, only the blue one. Sorry, I'm getting confused because my cat is jumping on the table. So if we fold it over this blue diagonal, we will have line symmetry. But if we fold it over the orange one, we wouldn't. So we have line symmetry over one diagonal, and that's a feature of a kite. So these are kind of the three main subclasses of quadrilaterals. We have, well, there's the nothing, right? Quadrilaterals that are just four sides that none are equal, none are parallel, it has no interesting features. Then our three kind of special subfamilies are parallelograms, which you can also within that have rectangles, rhombi, and squares. So if you don't know, this rhombus plural is rhombi. It's a good word to know. That's the plural of rhombus, not rhombuses. And then, sorry, sidetrack. So parallelograms, you could have a rectangle or a rhombus, and then a square is both of those. So one thing to take away from this that I saw some confusion on with some of our sometimes always never questions earlier is that squares are all rhombi. Rhombi are all parallelograms. Parallelograms are all quadrilaterals. They're like subsets, kind of like how a triangle that is isosceles, or sorry, triangle that's equilateral is also isosceles. That's just not its most specific name. So equilateral triangles are always isosceles, but if we ask to classify it, we always want to use the most specific name. The exact same thing applies here. All squares are rhombi, but if I give you a shape that is a square, I don't want you to classify it as a rhombus because that's less specific. So when we have a shape, we always want to use the most specific name possible. Then we have our trapezoid subfamily, where we have exactly one pair of parallel sides. Those could be isosceles trapezoids where the legs are congruent. And then we have kites, which have diagonal symmetry, or line symmetry over one diagonal, and where we have the two pairs of congruent sides, but they are consecutive, not opposite, like they are on a parallelogram. All right, so that's our general quadrilateral family, and then we'll spend some time day by day going into each one of these specifically and talking more about their mathematical properties and how we can set up and solve problems with them.